So welcome everybody. We are now at week 9 of NTU semester 1, and we are now going to chapter 7, and it's called least squares and normal equations, and we'll complete everything in 2 hours. So it'll be 1 hour today and 1 hour on Friday, and then in that we can then do complex numbers if we are going to do something on complex numbers. So that's about it. So let's do least squares and normal equations today. So least squares and normal equations. Now, let's see the lecture notes. In least squares, the number of slides are relatively few. There's only 7.1.1 until 7.2.1. So the problem that we are going to see very quickly is this problem. We're going to have a matrix that is tall, m rows is greater than n columns. And typically, this is the problem in machine learning. All right, let's write down. So we have ax equals to b, and we are given a, and we are given b, and the problem is to find x. And a is the dimension of R, m by n, and then we write it this way. We have m rows and n column. Let's say a1 until an. So n columns. And if a looks like this, oops. Okay, guys, you all have to warn me. All right, if I'm not showing you the screen. The screen's okay now, guys? Yes? Thank you. So you have m rows and n columns, and x, of course, then become x1 to xn. And then we have b1 to bn. All right, so this is the tall matrix. That's the jargon in the street. We have a tall matrix, and we want to solve for the x. And what are the problems, guys? So let's try the simplest case first. B belongs to the column space of A. So please participate. When the vector B is in the column space of A, what can we conclude? Quiz question. X can be found or cannot be found? I repeat, when B is in the column space of A, X, this equation can be satisfied by a given X. Yes, X can be found. That means X exists. Now the second question, is X unique, or is X unique, or there is infinite X to satisfy AX equals to B? X can be found, so EX depends on rank of A. Excellent. So yes, so X is unique if what? X is unique if no free variable. That means when we reduce A, there's no free variable. X is what? Infinite solution if free variable. The last one, when B is in a column space of A, then when we do Gaussian elimination, what can we see in A? A, after Gaussian elimination, what will we see? The augmented matrix A and B. After Gaussian elimination will become? Guys, what will we see here? Pivot in every column? Yes. But yes, pivot in every column means that what? There is no free variable, but this is what we'll see. 0 at the bottom means that consistent equation. Okay, so you realize that even in this very, very simple example of a tall matrix, and we have to draw so many different conclusions. Okay, let's do the second one now. Ax equals to b. If b does not belong to the column space of A, what can we conclude? Conclusions? No solution. Yes. A, x can never equals to b. No x satisfy this equation. That's one. Two, inconsistent equation. Inconsistent. Yes, because when we do Gaussian elimination, of A and B, what would happen, guys? What will we see? Gaussian elimination. We have what we see at the bottom. 0 equals to some number that is not 0. Okay? So, so this is how we know that the system of solution is not consistent. All right. Now, then what can we do? What can we do for inconsistent system of equation? Find the closest approximation to x. Very good. Outstanding. All right. I'm going to draw this plane is the W subspace. W is spanned by some A1, A2, for example. And we put A1, A2 here. A1 and A2. And we call this A. What else can we say about A? I'm giving you the names. W is a span of A1, A2. I put A1, A2 as A. I can say what? Typically, I like to say what? W equals to the W is a subspace, the column space of A, right, guys? Yeah, so now I now have a vector called B. And B needs to be approximate. Approximate B using A. So this is my A. So what can I do, guys? So it is A times X equals to B, the same problem. But if this picture already clearly shows that if I have given you A, then all you can run around is this subspace A, this plane over here. Now, if this is the plane over here, what is the best I can do? So I will find the closest approximation of B on the surface of W. I drop it here. And then this is B hat. B hat B hat equals to some AX hat. Some cannot, huh? There's no way. There's no way because B does not belong to the column space of A. So instead, I want to solve for AX hat equals to B hat. So what I'm trying to solve now is instead of finding along the space of W for B, I'm finding in the space of W for B hat. And B hat is sitting in on W, so I can solve this equation. So this is no problem at all. All right, now, what do we call this vector? Can someone type, please? What do we call this vector? Error. So it is E error plus B hat equals to B. Therefore, error is equals to B minus B hat. What's so special about the error vector? E equals to error. What's the cool idea about the error vector? How is the error vector related to the columns of A? That's what I'm asking. So, quiz question. How is the error vector is orthogonal? Very good. Error vector E is orthogonal to who? To what? To, yes, the W subspace. W space, that's one way. What else? Any linear combination of what? A, columns of A, right? Yes. And we can also say error is an element of W what? Perp. So you see, guys, we're saying a lot of things here. So you realize that linear algebra is difficult because it has a lot of terms that can be used interchangeably. All right. Now when I say this, right? Error is perpendicular orthogonal. So it says orthogonal is perpendicular, right? Perpendicular to any linear combination. How can I write linear combinations of columns of A? What notations would I use? Linear combinations of the columns of A. Guys? N. Yeah, but I want to write A what? X. Isn't AX a linear combinations of columns of A? Because you look at this. Come, guys. A1, A2. Let's be lazy, okay? I'm just lazy. All right, I'm just going to write two of them. X1 and X2. See? So isn't this a linear combination? Isn't this a linear combination of A? This is X1 times A1 plus X2 times A2. And by varying X, I can go anywhere along the column space of A. Okay, so this is what I'm talking about. All right, so we're almost there now. We are going to take this idea, the error vector is, we're going to take this idea, okay, and we're going to write an equation for this idea. Okay, E is perpendicular to the columns of A. Okay, I can write columns of A is perpendicular to E, right? No change, huh? E is perpendicular. So what else can I write? Who is the columns of A in dot product? Remember, if they are perpendicular, if U is perpendicular to V, then what will happen? U and V are perpendicular. Then U dot V equals to 0. Okay, what else can I write about u dot v, guys, in another notation? U dot v is one notation. Very good. U transpose v. Right. Okay, so take this. Now I'm going to write columns of A are perpendicular to E. Who are the columns of A? Columns of A is A1, A2, right? And at the AN. These are columns of A. I'm going to use this notation and say A1 transpose V. So A1 transpose E equals to what, guys? The columns of A are perpendicular to E. I'm going to use the first column and test against E. What's my answer? It's excellent. And of course, I can write the second guy, right? Which is also 0. And I can write until AN. Okay? So what have I just run? I have just written A transpose E equals to 0. Right? What is E again? E equals to B minus what? Let's go up. E equals to B minus B hat. This one. B hat equals to? B hat equals to this. So B minus B hat. B minus A x hat. So far okay? And now I'm going to substitute A transpose B minus A x hat. And now I open up the bracket. A transpose B minus A transpose AX hat equals to 0. Therefore, A transpose AX hat equals to A transpose B. And this is the all-important question formula. It is called the normal equation we derive. Now, what does this tell us, guys? Number one, what does this tell us? What does this equation tell us? So my quiz question is, can we solve for x? Does the solution always exist for x hat? X hat is what? Exists or not? Does not exist? Exists always? I repeat, we derive the normal equation. The normal equation tells us A transpose A x hat equals to A transpose B. Therefore, there is, what do we know, guys? What are we given? We are given A, right? So all the A transpose exists. A is known, A transpose is known. A transpose is known, B is known. Therefore, the only guy that is unknown is this guy. And therefore, we are able to solve. So it exists always, not question mark. We can always find x hat. And then some of y'all will be wondering, if A transpose A inverse does not exist, then what happened? Okay? Then what? All right, we'll come to it. So the take-home message is this. We have derived the normal equation from first principle and we come out with an equality. Okay, equality. Left-hand side equals to right-hand side. All the variables are sitting there and the only variable unknown is x hat. We can solve for x hat, even if A transpose A is not invertible. Okay, let us see why. All right, let's see why, guys. Let's have a simple example first to convince you. A equals to 1, 1. B equals to 1. All right, guys, let's play with this. I have given you one equation. How many unknowns? I've given one equation and how many unknowns? Two unknowns. So in fact, there's infinite solution, right, guys? So the number of solution is infinite because I can choose 1 times something x1 plus 1 times x2 equals to, I can choose different x1 and x2. I have infinite solution. Now, what happened here? What have I just done to the equation? I given you the second equation. I have made my system of equation what? What's the word I want to ask? Inconsistent, right? Because see, 1, 1 equals to 1. 1, 1 is also equals to 2. The system of equation is inconsistent, right? And therefore, now it's a least squares, right? All right, but never mind. Let's proceed to make a tall matrix first. 1, 1 again. Wow. 1, 1 again. And then what do you think I'm going to write here, guys? What do you think I will write here? 0. Yeah, 0 will be good. Okay, well, it's always 1, 2, 3. I have no idea why. So the system of equation is still inconsistent. But now let's proceed. We are trying to solve ax equals to b, find x, right? Find x such that what? The norm of the error is the smallest. So that's why smallest means what? Least squares. Okay, that's why the word least squares. So remember, we play with this. We make the normal equation. A transpose A, x. So we left multiply by A transpose. Therefore, the right left multiply by A transpose on the right hand side. Can? So later on you realize that, hey, A transpose A is not invertible because the columns of A are dependent. All right, never mind. 1, 1, 1. 1, 1, 1. This is A transpose. 1, 1, 1, 1, 1, 1. And then we have x1, x2. And then we have 1, 1, 1, 1, 1, 1. And we have 1, 2, 3. Okay, let's solve. This guy, this is a 2 by 3. This is a 3 by 2. We'll get a 2 by 2. So this row multiplied by this row, the answer is 3. This row multiplied by this row is 3. 3, 3. Oh, the matrix A transpose A is rank 1 in this example, right? Only one independent column, one independent row. X1, X2. This guy, 3, 4, 5, 6. 6. So guys, I'm asking you, can we solve for X? Yes or no? No? Can? Cannot? Guys? Okay, what do you do when you're here, right? What will you do? You would become 3, 3, 6. 3, 3, 6. Then you'll become 3, 3, 6, 0, 0, 0. Consistent, right, guys? And then you'll become 1, 1, 2, 0, 0, 0. And then your answer is X. Then you have only one what do you call it? One pivot, one free. So you make a free 0, x is equals to, x1 is equals to 2, x2 equals to 0. So x0, sorry, x1, x2 is equals to 2, 0 plus the variable and then what? Minus 1, 1, I think. This is the general solution for x1, x2. Okay, guys, did I make it correct? Yes? Everybody? So we are happy. We are happy because even though the system of equation is inconsistent, and if we have started from here, we have never solved it, by doing this little magic, by pre-multiplying on the left by A transpose, the normal equation, which is this guy, can be solvable for any x. So by just pre-multiplying by A transpose B, we have forced this guy. Originally, B was not in the column space of A. It's obvious. B is not any linear combinations of A. But by multiplying by A transpose, 6, 6, and become this guy, this A transpose B, is now in the column space of A transpose A. That's the magic. Okay? And why is this so? Because of this property. There. This is an equality, right? Therefore, we can always find a x hat such that we can multiply by the column space of A transpose A to get A transpose B. That's the key idea. So normal equations is wonderful. All right. Now, if 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 you are going to be doing MATLAB, right, guys? And honestly, you have to do MATLAB. Just use it as a calculator, please. So I'm going to show you how to do MATLAB as a calculator. Okay. A equals to, what's my A again? 1, 1. 1, 1, 1, 1. That's my A. B equals to 1, 2, 3 prime. And X is equals to I mean, what do you think I will write? So it is actually A backslash B, which is giving you the least square solution. 2, 0. Okay, so that's my answer. Now, some tricks. A times A transpose A. Okay, I got this number correct. A transpose A. A transpose B, 6, 6. I got it correct. And someone will ask me, can I do inverse of A transpose A? And then if A transpose A is 3 by 3. So if I do inverse of this matrix, you'll see that you'll warn me. Okay, infinite. Okay, so we are using MATLAB as simply a calculator to check our workings. All right, so if you're happy with this, then I'm going to proceed to the next example. Okay. Next example. Same. A is equals to 1, 1, 1. B equals to 1, 2, 3. All right, my question to you guys is this. I have given you a column of A. And of course, you are going to say, we are going to solve AX equals to B. And then if you look at this picture, you will be thinking, since I've only given you one column, A1 times X1 equals to B. And then you say, there is no way. right? There is no way that I can multiply some numbers and it will be this. So what am I asking for, guys? This help? What am I asking for now? These squares, yes? But yeah. So actually the idea of this picture is this, huh? Imagine this is the vector 1, 1, 1. And imagine this is the vector 1, 2, 3. What am I? Yeah, make x to make the smallest error. So what am I trying to multiply? Okay, I should be writing them as vectors so that you can clearly see. So this is the b vector, right? So this is the b vector, blue, right? The v vector is sitting here, and the a vector is sitting here. I'm talking about abstractly, yeah? So x1 is a scalar. So this guy is a scalar. So what can a scalar do to a vector, guys? He can multiply positive and he will land up here, right? Make it bigger. He can multiply negative and he will land up here at the back. So I can choose. Positive x, I will extend him this way. Negative x, I will extend him backwards. So I'm trying to find the best x1 to extend, right? Extend who? Extend a1 such that a1 x1 will become who? Come b hat. Who is b hat? This point here is b hat. B hat, yes, orthogonal projection. See, I am projecting orthogonally B onto the what, guys? What is this blue line called? This blue line is a what? The span of A1, right? Yeah, see? A is here. I can multiply. So this whole dot line is the span of A1. So if you look at the last lecture, in fact, this is the simple version of least squares. I'm projecting my B onto a single vector. Right. So you know that, hey, we are not going to solve this problem this way. Okay. Let me give you one, any problem if I only give you one. Okay, let's not talk about the values of this first. Any problems with first equation? 1, 1 equals to 1. Sorry, the first element 1, second element 1, b is 1. Any problems with this equation? Consistent or inconsistent? No problem. Yeah, no problem. I'm just giving you one equation with two unknowns. By the time I give you the second number, any problem? I give you a pair of equations. Yes. And the problem is the system of equation become inconsistent. 1, 1 equals to 1, 1, 1 equals to 2. Of course, inconsistent. Right. Now, what about the columns? The columns of A1 in the previous example, the columns of A1 was the same as the columns of A2. That's why A transpose A couldn't be inverted. Let's try a different story now. What number do you think I will put here? Here in this little box here. 0. Yeah, why you guys like 0, huh? Yeah, 0 is okay, but I'm going to try -1, okay? I'll try -1. Now, is A1 and A2, are they are they are they what, lying on the same line? No, because A1 and A2 are independent. Okay, they are independent. And therefore now I can do a lot of things. So let's try. Ax equals to B, introduce the normal equation, A transpose B, and now my A is 1, 1, 1, 1, 1 minus 1. Multiply by 1, 1, 1, 1, 1 minus 1. My x, 1, 1, 1, 1, 1 minus 1. My b, 1, 2, 3. And then, so my equation now becomes 1, 1, 1, 1, 1, 1 is 3. 1, 1, 1, 1, 1 minus 1 is, oh, I can't do this. 1, okay, right? 1, 1, 1 times 1, 1 minus 1 is 2 minus 1 is 1, correct. 1, 1 minus 1, 1, 1, 1 is 1, and here is 3. Notice that A transpose A is a what matrix, guys? It's a square matrix. What else? Symmetric matrix. Okay? And symmetric matrix have very nice properties later on you'll see. All right. And we have this times x equals to, what's my right hand side? 1, 1, 1 times 1, 2, 3 is 3, 4, 5, 6. And I have 0. So again, now I write the augmented matrix. 3, 1, 1, 3, 6, 0. And you perform Gaussian elimination and you can find the solution. That's one way. That was the previous way we did because we were stuck, right? We were stuck because there was no way. There was no way we can perform A transpose A inverse. We were stuck. We have to do Gaussian elimination. But here, actually, we don't need. We don't need. This one, yes, can be done, but it's not as oops. So instead, I want to do it this way, implying A transpose AX equals to A transpose B. This guy, A transpose A, you look at him, you look at this matrix. Is it invertible? Is it rank 2? Yes. This first column and this second column are independent. So A transpose AX is. So I can do A transpose A inverse. It exists, right? And I'm going to multiply by this guy. A transpose A X equals to, since I multiply on the left, A transpose A inverse A transpose B. And this guy becomes I, therefore it left out with X equals to this famous equation over here. X is equals to A transpose A inverse A transpose B. And the reason why we can do this is, in A transpose A invertible. This is the first reason. But why is it invertible? Because columns of A are what? Independent. And then third one, remember, guys, we are always talking about what? And third, we are talking about what kind of matrix? About what kind of A? What's this word I will put here? Square? Nope, not square. A is not square. A is not symmetric. Remember, we start with the whole picture of what is A? A is tall. Okay, when A is tall, we're playing this game. When A is square, we play a different game. When A is short and fat, we play a different game. Okay, so let me show you the slides. See? When A is tall, when A is square, almost square or square, and where A is fat. In machine learning, we are always playing with tall matrices, normally. Okay. Why do you think I say that, guys? Why do you think we're talking about tall A? Let's have a short, fat A. A is equals to 2 by 3. 1, 1, 1, 1, 1, 1. Can? B equals to? Give me some numbers, guys. If A is this, B equals to? No more 3, friend. The reason is since there's only 2 rows, there can be only 2 B's, right? Because AX equals to B. We're trying to find, right? What is X, guys? If A is 1, 1, 1, X must be X1, X2, and then X3, right? Since there are 3 columns. All right. Now let's try. Let's try our magic again. A transpose A, X equals to A transpose B. Agree? So far? We all think. What is A transpose A? This guy is 2 by 3. 2 by 3 matrix. This guy is 3 by 2, right? Because now I have a... So A transpose becomes tall. This guy is 2 by 3. Agree so far? So A transpose A is 3 by 3. Also a square, right, guys? Yes? But what? But something. But always what? Singular. Why? Because the rank of A is, this is M by N, is less than or equals to M. And now this square matrix is N by N. So there is no way, huh? We have no chance, right? If it is a fat matrix, we have no chance to go along this direction. Okay, there are other clever ways to do this, but not this way. All right. I think I'm almost done. This is all I'm really going to say. So let's revise very quickly what we have just spoken today. So in today's lecture, we studied primarily the least square solution. The least square solution we studied in detail in this 45 minutes, how to solve for a tall matrix A. And then we observe that if B is in the column space of A, then all these things are true. It says that if B is in the column space of A, AX can be equals to B because B is in the column space of A. And then we introduce some other little additional possibilities of whether X is unique or X is infinite. Now, of course, we come to the great picture of least squares. In the least squares, B is not in the column space of A. So AX can never be equals to B. This equation is wrong. The equality is wrong. Not possible. Why is it not possible? This is the nice picture. The red vector is B. The green square is the span of W. Means that I can be sitting anywhere along the W, but there's no way. Okay? So if I write the span, the basis as columns of A, then span of A1, A2 is simply A times X. Yeah, simply A times X. By A times X, I can go anywhere on the floor. And because I can only go anywhere on the floor, I have chosen to go to the place called B hat. And B hat can be there because, hey, it is nothing but A times X hat. And A times X hat means find anywhere on the floor. And then I find a place here such that the error vector is the smallest. And the smallest, because this is the Pythagoras theorem, this is one side, the short side. Because if I move away, it becomes a hypotenuse. Now, because I start with this E, the condition that E must be perpendicular to the space of W, I derive the normal equation. we derive the normal equation slowly, and we realize that, hey, the clever idea, we say that E is orthogonal to the column space of A. It also means that A transpose E equals to 0, because A transpose is flipping the columns into row. A transpose, the rows of A transpose is the columns of A. Then we substitute E, which is B minus AX, and then we derive the normal equation. And the beauty of the normal equation is this. This is an equality. It means that the only unknown x hat can be found. Always. X hat always exists. In the previous case, B is not in the column space of A. X can never be found. All we can do is get X, B hat. But by free multiplying with A transpose, we now can find a X hat, because X hat will land our vector AX hat onto exactly here. Okay? All right. So then I give you two examples. The first example is the trick example. The trick example is I given you an A that is tall, very nice, but unfortunately the columns of A are dependent. And when you work it out, A transpose A is not invertible, primarily because the columns are dependent. See? The columns are dependent. So there is no way I can perform A transpose A inverse. So your least squares equation, that little fancy equations that we play with, where's my fancy equation? Here, cannot be used because I cannot. But 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 we always remember that we can find x such that this equality is true. So we use Gaussian elimination, and we can really find x that solve for this. Okay, so this is always a trick question. All right, so the last statement is I've given you an A and now it's tall. I've given you a B that is not in the column space of A, and now I continue to work it out, the famous equation that I will apply, which is this. And voila, I can find A transpose A inverse because it is A transpose A is not singular. And it is not singular because it has independent columns of A to start with. And then we find the answer. All right. So I think I'm almost done. And Daryl and